Chapter 3.3, Function Notation and Evaluation. When we're dealing with a function, which you remember is each input going to exactly one output, there's a special notation, which means a special way of writing, that equips us with some useful options, and it's called function notation. We use this f of x. This is not f times x. We're not multiplying f and x. And that can get confusing when you start using different letters. I know that you're used to seeing this and thinking that means multiplication the same way that means multiplication. But no, with function notation, it does not mean multiply. This is read as f of x. F of x just means y. This is the same as y equals 5x minus 8. And so people ask the question, well, if it just means y, why not just use y? Because having this function notation lets us do a couple really quick and useful things that are helpful. First of all, it lets us know we have a function. So we know that whatever we plug in for x, there's only one possibility of getting something out for y. That confidence is very useful, knowing you have a function. But it also lets you very quickly see inputs and outputs. Whatever number I put in here, I call this the input hole, whatever number I plug into that little slot replaces all of the x's in the function. So this becomes 15 minus 8, which is 7. We just had f of 3 equals 7. Well, now we can see very quickly the input was 3, the output was 7. Inputs and outputs can be displayed quite nicely, whereas if we did this like y equals 5x minus 8, then we have to do, okay, so we say that x equals 3, so we do 5 times 3 minus 8, which is 15 minus 8, which is 7, so y equals 7 when x equals 3, and as we can't quite show it quite as cleanly and quickly as just right here. When x is 3, y is 7. Very nice. But we can also start kind of generating lists very quickly. It's a 4, and here's a 5. And I'm not going to show the work for this, but if I plug in a 2, I'm plugging a 2 in for this x. 5 times 2 is 10, minus 8 is 2. I plug in a 3 for this x. 5 times 3 is 15, minus 8 is 7. At this point, I have a slope of 5. Plug in a 4. 5 times 4 is 20, minus 8 is 12. The next one will be 17. We're going up by 5 because that's our slope. Well, here I have a whole table of inputs and a whole collection of outputs. And I can actually just make a quick little table. I plug in 2 for x, get out 2 for y. Plug in 3 for x, get out 7 for y. And I can quickly move from inputs to outputs, and that's very convenient. Another thing that functions let us do is label things. We don't always have to use f. We can use f and g and h and k and whatever we want. So now I can have multiple equations, multiple rules at the same time, and have them labeled very cleanly. So here's g of x, where g of x equals negative x squared minus x minus 2. And say I wanted to find g of negative 4. Well, this means I'm going to plug negative 4 in for this x and this x, for every x that you see. So now it's negative 4 squared minus negative 4 minus 2. There's a lot of negatives here on purpose. By order of operations, I do this first. I didn't circle that very well, so I will circle that better, and I'll change colors to make it more clear. I'm going to do this first. I square things first as order of operations. So it's going to give me a negative 16 plus 4 minus 2. Negative 16 plus 4 is negative 12, minus 2 is negative 14. So g of negative 4 is negative 14. And if I were to do something like g of, that was a y, g of Sam. G of Sam would be negative Sam squared minus Sam minus 2. And if I were to do something like g of 3 plus k, I would plug a 3 plus k in here and here. So it would be negative 3 plus k squared minus 3 plus k minus 2. Now we would never do g of Sam unless we had some weird function defined where Sam could actually be an input, like maybe Sam got some points in a basketball game or something. But g of 3 plus k is very reasonable and quite common. They don't have to be f's and g's, they don't have to be x's. This is h of t, and maybe h stands for height, and that's usually our y value, but now we're calling it our f of x value, or our h of t value. And t stands for time, which is usually our x value, our input, but this is a function that tells you how high something is if it's dropped from a height of 20 feet. Because things fall at negative 16 feet per second squared with gravity on Earth. It doesn't have to just be g's and f's. So there's really three main ways that we show relations. We use a graph, a function rule, and a table. But all three of these things are showing the same relationship. So let's say you owe your parents $5, and they give you $2 every week. Well, we could set that up with this rule. We owe $5, but we're getting 2 every week, so x stands for weeks. F of x stands for money we have, total money. We could show that graphically. But we could also plug in points and get out a table. Or we could use our table to create a graph with a really bad arrow on the end. Or we could look at our graph and go backwards and make a table. And this one's usually the trickiest, but if we wanted to go from the graph itself to a function rule, we could. All three of these things, graph, function, and table, are showing the same relation. They're all functions. They all have one input going to one output. It's just different things you can use to utilize things. Graphs are nice because they can give you a full picture of trends and individual points and what's happening. The issue with graphs is if you don't have the function itself, you can't necessarily find other points, or it can be tough to find other points. Functions are useful because you can see what's happening if you understand like what the trends are, by which I mean like if you know slope and y-intercept, you know it's going up 2 times every week and we start at -5. And from a function you can generate a table or a graph, but functions can't always show trends really, really clearly and visually like graphs can, which is nice about them. Tables can be really nice to analyze things. You can do a lot of good analysis with tables, see individual points really clearly. Sometimes a graph doesn't have clean, precise points, but a table does. All three of these things have their strengths and weaknesses, which is of course why we use all three. If there was something that was just perfect, we would just use that one perfect thing, but there's strengths and weaknesses. Also notice this was discrete, because we're not ever going to get $4.2, we're just getting $2 more each week. So for x, we would just plug in whole numbers. Our domain for this would be whole numbers, which there's a big capital letter you can use for that, but let's just stick with whole. I suppose we could say integers because I'm going back in time. It's possible to go back in time. Here we could say 2 weeks ago we owed $9, and then a week ago we had 7. So maybe I'll go from whole to integers. The letter for that is a Z in case you cared, but that doesn't matter so much. So I can use this function notation with a table. Here is my table showing the relation of some new f of x. If the input is -3, that's what this is saying. If the input is -3, what's the output? 6. If the input is 6, the output is -3. Oh, that's kind of interesting. They're like inverses. If the inverse is if the input is 51.2, you get out 810. Now here I'm doing f of 4 plus f of 6. Well, f of 4 was 11. F of 6 is -3. We add those up, we get 8. Here I'm doing f of 4 plus 6. Well, 4 plus 6 is just 10. F of 10 is 12. So notice that f of 4 plus f of 6 is not going to be the same as f of 4 plus 6 necessarily. Plug stuff in for x, get stuff out for y, which we call f of x. That's function notation. It's fairly straightforward. We can do it with rules, we can do it with tables, and we can do it with graphs. Here, this is saying the input is 2. If the input is 2, what is the output? Well, that means I go to 2 on the x-axis, and the output is actually 0, so that's the point 2, 0. If the input is -6, I go to -6 on the x-axis, and I look for the corresponding point on the y-axis. This is the point -6, 1. The output is 1. If I'm doing f of 0, this is finding the y-intercept because the x value is 0. The input is 0, the x value is 0. That corresponds to a point of 4. And, I mean, I could do this for anything. F of 1 is also 4 because the input was 1, the output was 4. The graph just shows inputs and outputs. Every coordinate, every ordered pair has an input and an output attached to it. X is the input, Y is the output. Well, here I can find inputs and outputs. Now this is doing something different. In fact, pause this for a second and see if you can figure out what this problem is asking us to do. It's saying the y value is 4. The y value is 4. So what's the x value? What's the input? Where on the graph do we have y values of 4? That happens everywhere along this line. Meaning it's happening from -3 to 1. Everything in between -3 and 1. And I didn't actually write like -3 and 1, because what about like 1.8 or -0.3? There's a bunch of decimals that it could also be. So it's everything in between -3 and 1. If the y value is 2, what is the x value? If the y value is 2, that happens here and here. The x values are -5, and that is actually 1.5. It's not everything in between, so I'm just listing out those two things. If you're wondering how I knew that was 1.5, I didn't actually guess. This wasn't a guess. I'm not saying that it looks like 1.5. This has a slope of down 4, right 1. Every time it goes down 4, it goes right 1. But that also means every time it goes down 1, it goes right a quarter. It's proportional. So it's going down 1, right a quarter, down another 1, right another quarter. So it's going down 2, so that's 1/4, down 1, right a quarter. So it's going down 2, right a half. If I went right 1/2, I am at 1.5. Anywho, if the y value is 7, that never happens. We often here would say x is undefined. We can't say 0. If you say x is 0, that means that we're here. But that's not happening. So we can put this empty set or undefined. I think empty set is probably more appropriate here. So let's just do the domain and range while we're at it. The domain is going from -6 to 3. The range is going from -4 to 4. Function notation is a wonderful thing. Learn to use it and learn to love it. One of the reasons function notation is so wonderful is because we can label expressions and functions very clearly. Instead of calling everything a y equals, we can have like f and g and h and j and k and whatever letters we want to represent functions. And now I can work with these functions or with these expressions with their separate labels. So here, this is f plus g of x, which means just take f of x and g of x and add them up together. This is the mathy way of saying it. This is how we think about it, f of x plus g of x. So that's doing this plus this, so that's going to be 3x minus 1. And subtraction is doing this minus this, so here's f of x minus g of x. So you have to be careful with your distribution here. It's 4x plus 1 minus -x minus 2. And that this negative has to get distributed, so it's 4x plus x, which is 5x, and 1 plus 2, which is 3. So this becomes 5x plus 3. That's f of x minus g of x. I can also multiply them, which will require distribution, or foiling as you often think of it. I'm doing this. So 4x times -x, well, I'll write this out first. 4x plus 1 times -x minus 2. Negative 4x squared minus 8x minus x minus 2. So it's negative 4x squared minus 9x minus 2. We aren't going to delve too far into division in this chapter. We'll talk a lot more about division in another chapter. With division, you just literally put one on top of the other. You divide them. So we're going to have 4x plus 1 over -x minus 2. And we've talked about this before, but you can't cancel these 4s. You can't cancel these x's. You can't cancel parts of things that have addition or subtraction to them. Ooh. Okay, could write that out better. So right now, this can't simplify any further. We do say that x cannot be -2. We have to express that x can't be -2, because if x is -2, this becomes +2, and +2 minus 2 is 0, and everyone knows thou shalt not divide by 0. But like I said, that's not something to worry about too much right now. I just want you to see that, because in a later chapter, we'll talk about that a lot. Add, subtract, multiply, divide with functions, but you can also compose them. This is function composition. What that means is you're going to take one function and put it inside another. That's what this open circle means. That's not an O. That's like an actual, just a symbol. The open circle means composition. this is read f composed with g, or we say f of g. It looks like fog, but it's not fog, it's f of g of x. This means I'm going to take the g of x function and plug it in to f. So up here, I'm literally, come on, get big, thank you. I'm going to take all of this is the g of x function, and plug it into this x right here. I'm doing f of g of x, so it becomes 4 times negative x minus 2 plus 1. That is what's happening down here. Paste it slowly. I'm taking g and plugging it into f. I mean, think about all the times I've had us do like f of dog, which became 4 dog minus, or 4 dog plus 1. Or like f of a, which is 4a plus 1. Well, now we're doing f of g of x. We're taking g of x and we're plugging it into f. We can do that with variables, or we can do it with numbers. This is f of g of negative 2. This means first you find g of negative 2, then you find f of that. So this equal sign is a little bit confusing. All this stuff goes together. First you find g of negative 2, then you find f of that. So g of negative 2, we actually just talked about, it's 0. So I do f of 0, and f of x was 4x plus 1. So I'm doing 4 times 0 plus 1, and that gets me 1. So f of g of negative 2 is just 1. If you wanted to take that open circle and turn it into a parenthesis like this, it's like you're doing f of g of negative 2. So I'll do some more examples with this. I've got 4 new functions now, well, 2 new functions, a and b, with 4 problems going with them. A of b of x is what this is saying. A of b of x, or a composed with b of x. I'm going to take the b of x function and plug it in here for a. So I'm really doing a of 3x squared. And a of 3x squared, I know it looks like a times 3x squared, but I'm sorry, it's not. It's a of 3x squared. I'm plugging 3x squared into this x. So it's really going to be 10 times 3x squared, which is 30x squared. I took the 3x squared and plugged into that x. So now a of b of 4, I have 2 options. One option is just first find b of 4. And b of 4 is 16 times 3, which is 48. Then I can just do a of 48. You plug in the result to the a function. A of 48 is 480. Or I could do another option. I could take, I know this right here was a of b of x. I know that a of b of x was 30x squared. So that means a of b of 4 is 30 times 4 squared. 4 squared is 16. 16 times 30 is 480. You'll always get the same thing if you've done it correctly. Now we flip it around, b of a of x. So I'm going to take the the a stuff gets plugged into b. This is going to go here into just the x. Just the x is getting replaced. So this is really going to become b of 10x. And b of 10x is going to be 3 times 10x squared, which is 3 times 100x squared, which is 300x squared. So to do b of a of 4, first I could find a of 4. A of 4 is 40. I just wrote a to the 4th. That was silly. A of 4 is 40. So b of 40, well, 40 squared is 1600 times 3 is 4800. Or I could just plug a 4 into this x up here. 4 squared is 16. 16 times 300 is 4800. That was a box, not a 1. 4800. Function composition, another useful thing to do with functions, of which there are many. Thanks for sticking around. Hey, you did it. You watched a whole math video, or you at least skipped to the end here. Either way, thanks for watching. I hope it was helpful. If it was helpful, maybe share it with a friend in your class who could also use it. You can subscribe to follow more videos. You'll see links popping up in the corners to watch previous and past and good videos. You can always leave a question down below or just add a comment. And I hope you have a wonderful day. Thanks for watching.